Welcome back to the deep dive. Today we are tackling a subject that sounds pretty technical on the surface, but I mean, if you have used any AI tool in the last 6 months, you have definitely felt the pain of this
Oh,
personally.
absolutely. Every single day.
Right. You know that moment when you ask, you ask a model a question that requires just a little bit of actual detective work?
Yeah, like connecting to obscure facts or something.
Exactly. Or solving a logic puzzle. And it gives you an answer that is incredibly confident, grammatically perfect, and just completely, utterly wrong.
The confident hallucination.
Yes.
It is the Achilles heel of the current AI boom right now. I mean, it's the difference between a tool that is fun to play with and a tool you can actually trust with your job.
It's like that friend at a party who answers every trivia question instantly, even when they have absolutely no idea what they're talking
We
about.
all know that guy.
Right. But today, we aren't just complaining about it, we are actually looking at a fix.
A very specific fix.
A very sophisticated one, too. We are doing a deep dive into a framework called Think on Graph 2.0.
Or TOG2 for short.
Right. And this isn't just a software patch either.
No, this is a fundamental rethinking of how large language models actually retrieve information. We are looking at a paper titled Think on Graph 2.0, Deep and Faithful Large Language Model Reasoning with Knowledge-Guided Retrieval-Augmented Generation.
Which is quite a mouthful.
It really is. It comes from a coalition of researchers, including folks from Idea Research and Renmin University of China. And their whole mission is right there in the title, deep and faithful.
Faithful is an interesting word to use in computer science. It implies trust. It implies sticking to the actual truth.
That is exactly the goal here.
Yeah.
We want to move away from AI that just predicts the next likely word and move toward AI that reasons based on verified facts.
Yep.
So our mission for this deep dive is to basically tear apart the methodology of TOG2.
We want to see how the sausage is made.
Exactly. We aren't just going to look at the test scores at the end. We want to understand the mechanics. Like, how did they engineer a system that combines the rigid logic of a database with the messy creativity of a language model?
Right. But before we get into the solution, I think we have to deeply understand the problem they're trying to solve. Most of you listening have probably heard the term RGAG.
Retrieval-augmented generation.
Right. It's the industry standard right now. You give the AI a library of documents, and when you ask a question, it looks up the answer and summarizes it. It sounds completely foolproof on paper. Why is it broken?
It feels foolproof because we imagine the AI reads the same way we do. But it doesn't. To understand why ARG fails on complex questions, we have to look at vector search.
Okay, vectors. We hear this buzzword constantly, vector databases, embeddings. But let's be real, if you asked me to draw a vector search, I would struggle. What is the system actually doing under the hood?
Okay, so think of a vector space, like a massive multidimensional library. But instead of organizing books by the Dewey Decimal System or by author name, the computer turns every single sentence or paragraph into a set of coordinates, a really long string of numbers.
So the cat sat on the mat becomes a list of numbers.
Precisely. And the feline rested on the rug gets a different list of numbers.
Okay.
And here's the magic of current RAG systems. Those two lists of numbers will be very close to each other in that mathematical space.
Mm-hmm.
The computer understands that cat and feline are neighbors. They share a semantic neighborhood.
Okay, so it is
Yeah.
looking for meaning, not just matching the exact keyword cat. That sounds pretty smart, actually. So why is that a problem for complex reasoning?
Because it is entirely proximity-based. It is great at finding things that mean the same thing. It is terrible at finding things that are logically connected but look completely different.
Can you give me an example of that?
Yeah, let's look at the specific example the researchers use in the methodology section of the paper. It is a question about a runner. The question is, where was one of the runners born who almost broke Craig Virgin's Illinois boys cross-country record?
Okay, wow. That is not a simple, what is the capital of France kind of question.
No, it's a puzzle. It is what we call a multi-hop reasoning problem.
Because you have to hop from one fact to another.
Exactly. To answer it, think about the logical steps a human would take.
Mm-hmm.
Step 1, who is Craig Virgin? Step 2, what is his specific record? Step 3, find the list of people who almost broke it. Step 4, identify the specific runner, which turns out to be a guy named Lucas Furzbicas.
Okay, and then step 5, you finally find out where Lucas was born.
Right. Now imagine doing that with vector search. You type in that full question.
Yeah.
The system turns Craig Virgin and record into numbers. It shines a flashlight into the vector library to see what is nearby. What did it find?
It probably finds Craig Virgin's biography.
Yes, or news articles about his record from 1972.
But does it find Lucas Furzbicas?
Probably not, because Lucas is a completely different person. His vector is mathematically miles away in that space. And the actual answer of the Lithuania where he was born is in a completely different galaxy.
Because Lithuania has nothing to do with Craig Virgin directly.
Exactly. A standard vector search sees Craig Virgin and just grabs documents near him. It doesn't know it needs to build a bridge to Lucas and then another separate bridge to Lithuania.
It sees the dots, but it is totally blind to the lines connecting them.
That is the perfect way to put it. The paper calls this the fragmented information problem. Text-based RAG is great at fetching paragraphs that look like your question, but it really struggles to track logical chains across scattered pieces of information.
So the industry realized this and said, okay, text is too messy. Let's use a knowledge graph instead. Let's define that really quick. A knowledge graph, or KG, is basically a structured map, right?
Yes. Think of it as a giant spider web. You have nodes, which are entities like people, places, or things, and you have edges, which are the lines connecting them.
So you have a node for Paris and a node for France, and the line between them is labeled as capital of.
Exactly. It is rigid, structured logic.
So if we have a map like that, why doesn't that just solve the Craig Virgin problem entirely? That sounds like exactly what we need to build those bridges. A leads to B leads to C.
It solves the structure problem for sure, but it introduces a brand new one, which is incompleteness. Knowledge graphs are skeletal. They have the facts that fit into neat little triples.
Triples being subject, verb, object.
Right. But they lack the flesh.
The flesh being the actual rich detail in the text.
Yes. A knowledge graph might tell you Lucas Verzbikas attended Carl Sandburg High School.
Yeah.
But it probably will not have the paragraph of text describing the specific race conditions on the day he almost broke the record, or the nuance of just how close he actually came.
So the text has the detail but no map. And the graph has the map but no detail.
Correct. And this leads us to what the paper identifies as the loose coupling problem.
Loose coupling.
Yeah, people have tried to combine these two things before. They call it hybrid RAG. But usually it just means running a text search and running a graph search separately, and then just pasting the results together in the prompt for the AI.
Like submitting two separate reports to a boss and hoping they can figure out how they relate to each other?
Yes. It aggregates the output, but it doesn't actually improve the search process itself. The text search isn't getting any smarter because of the graph, and the graph search isn't getting any smarter because of the text. They're just strangers passing in the night.
Which brings us to TOJI 2. The framework we are discussing today aims to fix that exact problem.
Yes, with what they call tight coupling.
Tight coupling.
Yeah.
So instead of adding them together, we are multiplying them. Graph times text.
That is the core innovation of the methodology. It is a collaborative cycle. In TOJI 2, the knowledge graph guides the text search by telling it where to look. And crucially, the text refines the graph search by telling it what is actually relevant.
It creates an iterative reasoning engine.
Exactly. It doesn't just look once. It performs rounds of investigation, getting smarter with each step.
I really like the comparison the paper makes to human problem solving here. It talks about a reasoning trajectory.
Yeah, they reference human cognitive processes. When you or I solve a complex problem, we don't just download a Wikipedia page and stare at it. We function like detectives.
Right. We find a clue. That clue reminds us of a person. We look up that person. That gives us a new location.
And we look up the location. We are constantly examining clues, associating potential entities based on our existing knowledge, and digging deeper until we find the answer. TOJI 2 is mathematically designed to mechanically replicate that human detective process.
All right, let's put on our detective hats then. I want to walk through this methodology step by step because the paper breaks this down very clearly and we really need to capture the nuance of each stage. So step one in their process is initialization, setting the stage. We have our user question about Craig Virgin. What happens first?
The very first action the system needs to take is to ground the question in reality. It performs entity linking.
So it scans the user's question and identifies the key nouns, the entities, like Craig Virgin, Illinois, cross country.
Right. It is linking them to specific nodes in its knowledge graph. It's basically saying, okay, when the user says Craig Virgin, they mean node ID Q12345 in my database. It is finding its anchor points.
Got it. It's sticking a pin in the map.
But here's the first really crucial filter in the methodology. It performs a topic prune.
Topic prune, because not every entity in a sentence is actually useful for solving the mystery.
Exactly. If the question mentions Illinois, That is a huge, broad topic. If you start searching every connection to the state of Illinois, you're going to get overwhelmed immediately with Chicago politics and corn production and weather reports.
Right, you don't want to go down a rabbit hole about the state bird of Illinois when you are looking for a high school runner.
So the LLM evaluates the question and selects the topic entities, the absolute best starting points for the investigation. In this case, Craig Virgin is a much more specific and useful starting point than Illinois. The system prunes away the noise early on so it can focus.
Okay, so we have our starting point. We're standing on the Craig Virgin node on the map. What happens next? The paper mentions an initial check.
Yes, before it starts the heavy lifting, it does a quick flyover. It does a quick check and asks, is the information we already have enough to answer this?
Oh, so if it pulls a document that just explicitly says Craig Virgin's record was almost broken by Lucas Verzbickas, who was born in Lithuania, then boom, we are done.
Right. It answers immediately. No need to waste compute power.
Very efficient. But let's assume the answer isn't just sitting there, which is why we need this fancy system in the first place. Now we enter the main loop. Step 2, knowledge-guided graph search. We are on the map.
We are on the map. And this phase is about finding the path. It starts with a relation discovery.
So starting at the topic entity, which is Craig Virgin, the system looks at all the immediate connections in the graph.
Every single line connecting to him. It looks at outward paths where the entity goes to something else and inward paths where relations come back to the entity.
And for a famous person or a well-documented entity that could be hundreds or thousands of lines, right? Born in, went to school at one award, has sister ate a sandwich at.
Exactly. And this is where the exponential explosion usually happens in traditional graph searches. If you try to follow every single path, the data becomes unmanageable instantly.
The branching factor problem.
Yes. If you have 100 connections, and each of those has 100 connections in 2 steps, you have 10,000 nodes to look at. In 3 steps, you have 1,000,000.
The computer would just melt, or at least it would take an hour and $50 in API calls to answer one question.
Exactly. So 2G2 introduces a mechanism called relation prune. This is a critical efficiency step. The system uses the LLM to look at the labels of these relationships and actually score them.
Score them based on what?
Based on the specific user question. It asks, given that the user wants to know about a record being broken, how relevant is this specific relationship path?
Okay, so if it sees a relationship labeled place of birth for Craig Virgin, it might score that really low.
Right, because knowing where Craig Virgin was born probably will not tell you who almost broke his record 30 years later. That is just biographical trivia.
But if it sees a relationship labeled participant in or competed against, that gets a high score.
Exactly. It is using common sense to navigate the graph. It is not just blind math. It is looking at the semantic meaning of the relationship. Only the high-scoring relations are kept.
That makes so much sense. So it keeps maybe the top 3 or 4 paths. And then what?
Then it does entity discovery. It follows those approved relations to find the connected entities, the next nodes in the chain. So it moves from Craig Virgin along the participant and path and lands on, say, the 1984 Summer Olympics or the Illinois State Championship.
Okay, so we have successfully moved one hop on the map. We have new suspect entities. Now we reach step 3, which the paper calls knowledge-guided context retrieval. And reading the methodology, this feels like the most distinct part of the whole framework.
This is the tight coupling part. This is where the magic really happens.
So for every new entity found in the graph, the system pulls up relevant documents to form a context pool.
Right. But how it searches for those documents is the secret sauce. This brings us to a technique called entity-guided context retrieval, or the triple sentence trick. Honestly, this is the part of the paper where I really had to sit back and think about how clever it is.
The triple sentence trick. It sounds like a grammar exercise. Walk me through it.
Okay, remember our graph. We have Craig Virgin, which is node A, connected to the 1984 Olympics, which is node B via the relationship competed in.
Right. Subject, predicate, object.
In a normal graph search that is just raw data, ID 123 connected to ID 456. But 2G2 forces the LLM to write that connection out as a natural language human sentence.
Oh, literally writing out the sentence, Craig Virgin competed in the 1984 Olympics.
Exactly.
Okay, I mean, sure. But why do that? We already knew that from the graph data. Why turn it back into regular English?
Because of what we talked about earlier with vector search. The system needs to find unstructured text documents to verify if this relationship is actually useful. If you just search your database for the keyword 1984 Olympics, you're going to get thousands of documents about swimming and gymnastics in the opening ceremony.
Massive noise.
Totally unhelpful noise. But if you search using that specific constructed triple sentence plus the original question, you're doing a knowledge-guided search.
Ah, I see. You are forcing the vector search to look for that specific intersection of concepts.
Bingo. You are using the structure of the graph to constrain the search of the text. You are telling the search engine, don't just give me general documents about the Olympics. Give me documents about the Olympics specifically in the context of Craig Virgin and broken records.
That is incredibly clever. It is basically using the graph to dynamically write a highly optimized Google search query.
That is exactly what it is. It isn't just searching for keywords, it is searching for the relationship described by the graph.
Okay, so it pulls these highly targeted documents. What happens next?
Now comes the reverse flow. Context-based entity prune. We just use a graph to find the text. Now we are going to use the text to judge the graph.
Judge the graph. How does that work?
The system asks, okay, we found these documents about the 1984 Olympics using our triple sentence. Do these documents actually match the intent of our original user query about a broken cross-country record?
And if the documents are just about him placing 12th in a 10,000-meter track event,
Then the system realizes this path is a dead end. Even though the graph confidently said there was a valid connection between Craig Virgin and the Olympics, the text reveals that connection isn't relevant to the specific nuance of the question we are trying to answer.
so what does it do with that entity?
It discards it. It prunes the 1984 Olympics entity entirely. If a connected entity has documents that match the query, well, the entity is kept. If the documents are irrelevant, the entity is thrown out.
The aha moment. The text is literally being used to prune the graph.
That is the tight coupling. This completely solves the graph incompleteness issue we talked about. Just because a database says two things are linked doesn't mean the link matters for your specific question. By letting the text vote on the graph nodes, the system ensures faithful reasoning.
So let's go back to our runner example. Maybe it followed a different path to an entity called Illinois High School Association. It pulls the documents using the triple sentence. Those documents talk heavily about state records and cross-country meets. The system says, jackpot, this text is highly relevant.
Exactly. So it keeps that entity. The high-scoring entities become the new starting points, the new topic entities for the next round of the loop.
Which brings us to step 4 in the methodology, reasoning with hybrid knowledge, the check-in.
Right at the end of an iteration, the system basically pauses and gathers everything it has found so far. It spreads all the evidence out on the table.
What exactly is it looking at during this assessment?
The LLM looks at three specific things. First, the retrieval feedback, which are the clues it summarized from previous rounds. Second, the triple paths, which is the structural map of how it got from A to B to C. And third, the top-ranked text chunks the actual paragraphs of rich detail it found.
Structure and detail together.
Yes. And then it does a sufficiency check. The LLM asks a very simple question. Is this information enough to answer the specific question the user asked?
And if the answer is yes,
Then it terminates the loop and generates the final answer. Lukas Versbikas, born in Kaunas, Lithuania. Case closed.
but if it says no, I still don't have the final piece of the puzzle.
If no, the LLM generates helpful clues. It basically writes a summary of what is known so far. Like, we know the record is in Illinois, we know it involves a high school association, but we still need a specific name of a runner. It uses that summary to create an optimized query for the next iteration.
And it dives right back into step 2.
Exactly. The new entities become a starting point and the cycle repeats.
How long does it keep doing that?
Up to a maximum depth set by the user. Usually about 3 hops is enough for even very complex logic questions.
I really want to pause and emphasize why each of these components matters, because the architecture is so deliberate, like the value of relation pruning in step 2.
Right. Without pruning, the graph search would explode exponentially.
And using the LLM to score those relations allows the system to essentially use common sense to navigate the graph rather than just blind math.
Absolutely. And the value of context-based entity pruning in step 3 is just as big. It forces the system to stay grounded in reality. Sometimes a knowledge graph says two things are linked, but the underlying text reveals the link is trivial.
It prevents hallucinations by constantly double-checking its map against the actual territory.
Yes, it enforces that faithful reasoning they put in the title of the paper.
And the value of the iteration itself. It allows for true multi-hop reasoning, solving problems where A leads to B and B leads to C, and you absolutely cannot find C unless you find B first. Vanilla search engines try to jump straight to C and they fail. 2G2 walks the path step by step.
It really is a massive leap forward in methodology.
Now, I want to zoom out a bit and talk about the assumptions made by the authors here, because this all sounds amazing, but engineering is always about trade-offs. What does this system actually rely on to function properly?
That is definitely the right question to ask. The authors are very transparent about the dependencies. First and foremost, the methodology assumes high entity linking quality.
Meaning the system has to be able to accurately identify the starting entities in your question.
Right. If you ask a question using heavy slang or a misspelled name or really vague reference that the system simply cannot link to a known node in its graph, well, the whole chain breaks before it even starts.
If it can't find the starting line, it can't run the race.
Exactly. Secondly, it assumes LLM capability.
What do you mean by that?
Well, we are asking the LLM to do some pretty sophisticated cognitive tasks here. We are asking it to score relations out of context, judge sufficiency of evidence, and generate optimized search queries.
Oh, I see. So if the underlying language model is too weak to understand the nuance of relation pruning, it might cut the wrong wire.
Right. It might prune the one clue that was actually going to lead to the answer. It requires a baseline level of intelligence in the model for the framework to actually yield results.
And what about the data itself?
Yes. The third big assumption is graph and text availability. It assumes a scenario where you actually have both a structured knowledge graph and an unstructured document corpus available to query.
Though the paper does note that graphs can be dynamically built from text if needed right.
They can, but the methodology clearly shines best when you have these two distinct sources already established.
Let's talk about the comparisons they make in the paper to other approaches, because I think this really highlights the value. We talked about vanilla RAG.
Right, vanilla RAG retrieves based on surface similarity.
Mm-hmm.
Toji 2 retrieves based on structural paths. Toji 2 wins easily on complex multi-step questions.
What about standard knowledge graph RAG, like the original TAG version 1?
Standard KGRG relies heavily on the graph being absolutely perfect and exhaustive. 2G2 uses text to compensate for any gaps or incompleteness in the graph.
And compared to the loose hybrid ARG models we mentioned earlier, like Coke,
Loose hybrids just run parallel searches and mix the results. 2G2 uses the graph to fundamentally improve how the text search is executed and uses the text to fundamentally improve how the graph search is executed.
a tight coupling.
Exactly.
Now, there is a finding in the paper regarding performance on smaller models that I think is completely shocking. They compared 2G2 running on Llama 2 to GPT 3.5.
Yes, this is the real David versus Goliath moment in the research.
For listeners who aren't deep in the model weight wars, let's set the stakes here. Llama 213B is considered a small model, right?
Very small. 13 billion parameters. You can run that locally on a high-end consumer laptop or a decent gaming PC.
And GPT 3.5 is a massive enterprise model.
Right. It lives in a giant data center and costs millions to train and run. It's a heavyweight.
But according to this paper, when you give the lightweight Llama model this think-on-graph framework, it actually performs at the level of the heavyweight.
It doesn't just match, it actually beats it on certain complex logic tasks. And this represents a huge philosophical shift. We have spent the last 5 years in AI thinking bigger is always better.
Right. More parameters, more data, massive brute force intelligence.
But Koji 2 suggests that a smaller brain with a superior process can beat a giant brain that is just relying on its internal memory to guess the answer.
Because the methodology does the heavy lifting.
Exactly. It relieves the burden on the model's internal parameters. The model doesn't need to memorize the entire world if it knows exactly how to systematically investigate a database.
I want to quickly touch on some implementation nuances from the methodology section before we wrap up. One thing that stood out is that Toji 2 is plug and play,
Yes, it is entirely training-free.
meaning you don't need to retrain or fine-tune your LLM to use this.
Right. It is a framework that sits on top of existing models. You just prompt the model to follow the steps.
And what about the pruning tools? The paper mentions an ablation study regarding how they actually do the pruning.
This is a really important nuance for any engineers listening. We talked a lot about the LLM scoring the entities and deciding which documents are relevant. The authors actually found that asking the main LLM to read and score every single document in the context pool is incredibly slow and expensive.
So how do they get around that?
They outsource it. They use a tool called a re-ranker.
A re-ranker.
Yes, it is a very small, highly specialized AI model trained to do basically one thing. It looks at a query and a document and instantly outputs a relevance score.
Ah, so it is much faster than an LLM.
Much faster and much cheaper.
Yeah.
So they use the big brain, the LLM, for the high-level reasoning and query generation, but they use the specialized tool, the re-ranker, for the rapid-fire pruning of the entities.
It balances accuracy with cost and speed perfectly. Okay, let's bring it home. We have covered a massive amount of ground today on this methodology. If you and I had to collaboratively summarize the exact flow of Toji 2 for someone who just tuned in, what are the key beats?
Okay, beat one initialization. Start with the entities in the user's question to find your anchor point on the graph.
Beat 2 relation discovery. Let the graph suggest logical paths forward.
Beat 3 context retrieval. Let the text validate those paths using the triple sentence trick to prune away irrelevant leads.
And beat 4 reasoning. The LLM checks if the puzzle is solved and repeats the whole cycle if it isn't.
That is the methodology in a nutshell.
And the core takeaway for why this matters.
The power lies entirely in the tight coupling. We have spent years treating structured graph data and unstructured text data as two completely separate worlds. Toji 2 proves that the real magic happens when you force them to talk to each other at every single step of the process.
Bridging the gap between rigid logic and rich detail. Before we sign off, I want to leave you, the listener, with a final provocative thought to mull over. We have been talking a lot today about this investigation process. As these systems get better at investigating rather than just blindly retrieving, how does that change our fundamental expectation of what AI is?
It really shifts the paradigm. We are moving from AI acting as a search engine to AI acting as an analyst.
Right. And if Toji 2 allows a small 13 billion parameter model to act like a massive data center model, doesn't this essentially democratize high-level AI reasoning?
I think it does. If a small model on your local server can out-reason a giant proprietary model simply because it uses a better investigative framework, then high-level AI analysis becomes accessible to anyone.
Hospitals, law firms, or just individuals who want to run advanced reasoning on their private data without sending it to the cloud.
Exactly. It shifts the power dynamic in the industry from who has the most GPUs to who has the most efficient reasoning methodology. We might literally be looking at the blueprint for the localized personal AI expert.
That is a future I am very ready for. It is not just about getting the right answer, it is about where and how the thinking actually happens. Thank you so much for breaking this down with us today. It is dense material, but incredibly exciting to look under the hood.
My pleasure. It is always great to dig into the actual mechanics of these breakthroughs.
To everyone listening, thanks for diving deep with us. Keep asking the hard questions and maybe use a graph to find the answers. We will see you on the next deep dive.